We're in a golden age for solar panels and home batteries, with prices coming down and adoption going up. The same hasn't been true for the wind turbine. This behind me is Harmony's vertical access wind turbine, and if you get in tight, you can kind of start to see some of the magic that makes this special. I've also learned a ton about the challenges of residential wind turbines and why we might finally start to see a golden age for that. So let's see if we can't figure this out together. I'm Ricky, and this is Tubine Vinci. This video is brought to you by Ecoflow. Harmony makes what's called the Savonius wind turbine. This is what it looks like. Imagine taking an oil barrel and cutting it in the middle and offsetting it, right? That's kind of what you've got. Now, their iconic design here has a helical component. And the reason for that is that way there's always some part, some scoop that is oriented to where the wind is coming from. So this was minimal stall, always be able to get started. You've actually built a wind tunnel to test some of these different designs and see how they perform.
Correct. Basically, we needed to look at a lot of different scoop geometries, variability in all kinds of things. Permutations from the performance is best suited at small scale because 3D printer technology can bang this out in 3 hours versus sitting there and building something for 3 weeks. You can't rate the turbine this way, but you can see how A compares to B. Right. And that's the big thing.
So we have just a classic,
Yep.
What do you call it, the half split?
Yeah, basically this would be your Savonius, your sort of a generic Savonius design, and that's what that one is right there.
So we're sitting around 2.3 volts, I'd say, right?
Right.
Let's try this one.
Okay.
What did you call this one again?
A Venturi effect fluid turbine, VEFT.
So this has a lot of the benefits of that classic Savonius with a little bit of maybe stall protection with a little
Yep.
bit more of a capture area.
Right.
But I'd say that's pretty much what we were seeing before, perhaps even a tiny bit higher.
Yep.
Although that would be much more difficult to machine.
And much more difficult to furl because you have no way of holding on to it. Like the top and bottom,
Oh.
there's no place for the gearing or anything to be.
So this is what we see a lot in the marketing and on your YouTube channel?
We call it our gold standard. We laughed about it after we realized we literally printed it in gold filament. So it's our gold standard that we've been showing for several years.
Yeah, let's see how it performs.
Yep.
So the idea was that you would be able to take in wind in any direction and never stall.
But it is not necessarily the best design, and the wind tunnel has proven that for us.
That does look really cool,
Yes.
but that's substantially lower.
Yes. So at some point, you've got to say, hey, it looks cool, but if it's not performing, in the end, it's all about the return on investment for the customer.
So what's really fascinating about engineering is as you see the bin, that's why I'm so glad you showed us the bin of all the trial and error. You can see the thought process.
Yeah.
You can see how this was approached. And I know what this was. This was, what if we get all the benefit of having the classic
Yep.
Savonius while having a little area allocated for catching wind in different directions to help with stalling, right? That's
Yep.
exactly what this
I know
is.
you're dying to put that one on.
I do want to try. I'm curious what the drop in performance would be.
Yeah, go ahead.
And if it would be worth it, right? Okay.
Yeah, we were trying to go for the increased performance that this would yield, but
Whoa.
yeah, I know. This is why it's so cool to be able to do this experimentation.
This is our best one yet.
Yeah, but that one would be a little bit difficult to make it work out there in full scale.
I'm trying to understand why this would be so much better.
These are all questions that many tens of thousands of dollars in a CFD laboratory would be able to explain. We don't have that, so our low-tech solution is our little wind tunnel here.
Shall we go check out the large scale?
Yep.
Okay. We go from 3D printed wind tunnel to
full scale. This is where we get to see the rubber meets the road here. Did what the wind tunnel showed actually perform in full scale? True Savonius turbines allow a little bit of the wind to come from the front that's catching and shuttle it through this gap to the one that's coming into the oncoming wind. So that helps to push it around a little bit further, a little bit faster.
Check this out. This is the next generation of batteries from our sponsor this week, Ecoflow. And as you can see, I've been using their batteries for years now. In fact, the Delta Pro 3, I took to Burning Man, and I used it to power everything from air conditioners, mini fridges, and microwaves. pretty amazing. But today I want to talk about these two. The Delta 3 Plus has a total of 13 output ports, 6 110 volt AC ports are up here, 2 36 watt USB-A ports, 2 140 watt USB-C ports, and a car power output. All in, the Delta 3 Plus can output 2600 watts thanks to its X-Boost technology. Charging is equally impressive. Plug into the wall and charge at 1500 watts in less than an hour. It even has 2 solar panel input ports, each good for 500 watts. In fact, we've got something powering it right now. Or in an emergency, it'll even charge via the Ecoflow dual fuel smart generator. With the optional extra batteries, you can extend this to 5 kilowatt hours of storage. But my favorite use case is using it as an uninterrupted power supply for our network equipment and internet modems. You can just plug it in, and in 10 milliseconds, it'll switch over and power anything in the event of a power outage. By the way, it even has storm warning mode, which will tell you when storms are upcoming to remember to top off the battery and be ready. And you can even set it to time of use mode to save your energy and use it when electricity is the most expensive and charge when it's less. And for the ultimate in portability, we have this, the River 3. It weighs just 7.8 pounds and you can take it with you anywhere. It has 2 AC ports with up to 300 watts in total, or 600 thanks to X-Boost. It has 2 USB-As and a 100 watt USB-C port as well. And with 245 watt hours of storage, you can fully charge my MacBook Pro about 2.5 times. You can charge either battery from the wall, from solar panels, from your car, or from a smart generator. The options are endless. The River 3 is drop proof from over 3 feet, and it has an IP54 waterproof rating. It's really durable and easy to take anywhere. There really is a battery for every use case. And if you want to learn more about Ecoflow's class-leading battery technologies, check out the links in the description. We also have some discount codes down below, and you can check it out for yourselves. Huge thanks to Ecoflow and you. Now back to the show. So this is the single drum. We also have the Helix designs over here, right?
Yes.
And you can just see how much more complex it gets because every one of these has its own sets of gears coming off the main shaft, its own furlings.
Yeah, and that all translates to cost of production. You know, the complexity, the time it would take to build it, the components we have to machine, all of that comes into play. This is one that I made back in the day in my basement. So this has the ability to do everything remote control.
So this is closing now?
Yep, it's closing. So we're 50% closed right there already.
Yeah, well, now it's becoming pretty obvious, I think.
Yeah. In the beginning, you know, like you can't even see when it's happening in the beginning.
Right.
So from 100% open to like 70% open, it's very hard to tell the difference.
So in the world of solar panels, we have ratings, right? We have your 300 watt panels, your 400, 500 watt panels. We have to achieve that level of marketing for the wind industry. So talk to us about the size and what do we got here?
Eventually, when we go into production, we will of course have the ratings on this. Our last step is certifying the turbines, finding the correct generator that'll be coupled with this to deal with the RPM range and the torque requirements that we have. But this should be mathematically about a 400 to 500 watt unit in a 25 mile an hour wind. This was actually the very second one. After this one was made, this was the next one.
You went from that to to right on.
Right, because we were, you know, I was really like only around 200 watts with that one, and I wanted to be somewhere up around a kilowatt. The width times the height is really what gives you that exposure to the wind, and then your efficiency is what tells you whether you're getting that or not.
Gotcha.
So,
but was this the test rig that you realized how powerful the full,
right now we have the
wind is coming on through.
Really whipping through here.
Yeah, 15 mile an hour wind right now is what we're seeing on the anemometer. And you can see that thing is really kicking. But by the way, these would be mounted 10 feet away from the ground, and then the whole entire rig is about 6 feet, but it would be out of the way. It's not like you're gonna actually interface with it.
Yeah, you can't hit your head on it or something.
Yeah. Can I do the furling here?
Yes, you can.
So here we've got the controls to furl and unfurl. I think this is...
Yep, it's so quiet you can't even hear it.
Yeah. So we're closing it down now. Yep. But I mean, there's a lot of engineering in all the gearing and controls and logic, right? All this is automatic.
Yes, it'll be basically monitoring its RPMs in a PID loop. So where do I want to be? If my RPMs are too high, I need to furl in for 5 seconds, and then it's going to check what its RPMs are in like 15 seconds or so.
This bulb now is pretty dim, and as we've brought in the furls, you can see that the RPM, the rotation of the system has come down. Now I'm gonna unfurl it and then we'll see. Nothing's changing with the airflow. The airflow is the same, but now we're unfurling it. He's holding the light. Look at how much brighter that got. It's just a little indication of the power output of this thing. That wind is really whipping through.
The thing that I want to impress right now is the generator is what's limiting us because of the RPMs. Like if you put your hand on this, I don't believe I could stop this without incredible amounts of force. So this is not meant to run in this really, really, really low RPM range. That's why that's all we're getting.
So one thing, you mentioned that the 500 watt rating is for wind speeds of 25 miles an hour.
Yeah.
What would that look like if you were getting 5 or 10 miles an hour?
You know, the goal is here at 25 miles an hour making 400 to 500 watts, but the hope is that you find the generator that would still allow you to make maybe 20 watts at that 7 mile an hour range. That would be great.
Got it.
So finding the right generator is going to be key to that.
So keeping in the trend of comparing with solar, this has moving parts unlike solar.
Yep.
Tell us about maintenance and some of those considerations.
So, of course, everything that we do here is trying to think of longevity and return on investment. One of them is the thrust bearing. In a vertical axis wind turbine, they're a major concern because in almost all vertical axis wind turbines out there, the thrust bearing is one of the main failure points in them. We have gone to, in the Mark III units, a magnetic bearing. We actually had started looking at doing it a while back, but you can see if I just lift up on it, see it lifting there? That is the magnetic bearing in here between two very large N45 magnets. So they're in opposition to one another, just like when you were a kid in grade school and put two of them on a pencil and they bounced. Same exact thing. The word on the street from the magnetic vendors and everything, basically you can have them in opposition like this for 50 years and it's not going to, you might get a slight degradation, so the air gap might decrease a little bit, but it's small percentage points. Everything that we do, we're trying to think of the ability to change it out in the field should it be necessary. Should there be something hits one of the scoops and damages it, you would be able to remove this whole scoop, put a new one in right in the field. You don't need to disassemble the whole unit. You don't need to take it anywhere to do that. So we have the thrust bearing, major point of failure that we hope we have addressed, appropriately or way more than other units out on the market. We've got one radial bearing up top and then another radial bearing at the bottom, but that's really your only points of, not even friction, but where your wear points would be. Cold weather, cold climate environments or severe environments would have to be sort of down the road. As we're in production, we'll determine what needs to be done for those environments. If we're getting a lot of interest in Alaska or Upper Canada where they need to deal with this, then we'll throw some money at researching that problem and coming up with solutions for it.
And you got to remember that for solar panels, same problems. If you have a snowstorm, you cover the panel and there's no production.
Right.
And you just got to wait until that clears up.
Right.
So some of these challenges are challenges even today for established things like solar. So how about price? What are you thinking about? And I know it's early.
Yeah, we're still in the prototype stage. So these are prototype numbers. They're going to be inflated. But if we can make them for 35, 36 and sell them for 6,000 or 65 early models, it's a decent profit margin there that we can keep the lights on, we can keep our people employed, and we can keep buying more materials to make new units.
All right, so let's go through the process of how we go from wind energy on this side, right? We've got ourselves some wind. And what has to happen in order for us to have, I'm gonna draw a little house here, and to go to electricity on this side.
Okay. Do you want me to fill in or do you want to draw?
Is that even a word? I thought it would get better the second time, and that's significantly.
I think it's too far to the side, but it's fine, dude.
Yeah, oh my God, that's even worse. This is the worst of the three. All right.
We have a vertical axis wind turbine, which is making rotational force. So you have a spinning shaft here that's rotating from the wind. Now you have that mechanical power. You then have to take that into a generator, which takes this rotational force and goes into electrical, what you call wild three-phase AC. So your wild three-phase AC is then basically coming out as 3 wires into your charge controller. Your charge controller then takes that and turns it into DC for you. So these guys are really, these two pieces right here are what we are trying to work out right now. We have this really under control, and we've had it under control for a while. Coming out of here, you've got your DC. So this is not a simple thing. Even though they exist all over the world, they're used for all different purposes. That's the hard part that we're on. So this DC then can go into a battery bank. It could go into a grid tie inverter, whatever you want to do for your home use.
Got it. So what's interesting is we could charge a battery, right?
Yep.
Directly with this. That's pretty good.
Yeah.
With DC. Or, to your point, we could go to an inverter.
Yep.
Inverter to then power your house.
Yes.
But the casual observer might be thinking, well, you just had AC right here. Why go through all of this to come back here again to, let's say, 60 hertz AC?
Yep. It's because the wind doesn't blow at a consistent speed. So you would get maybe 5 hertz, you'd get 80 hertz, any variation in that wind speed. Correct. Your lines might be super compressed or super opened up, and that your equipment in your home is not going to be happy with dirty power like that. It'll be seeing it as brownouts and all sorts of things, because you can't hold a constant AC in a variable condition like wind. So you need to take it into a buffer such as your DC or your battery bank, and then from that clean, stable source, you take it into your inverter. So you can even have a line coming down from your battery bank into your inverter, and then instead of going directly into here, you have a much more controlled source giving you clean power to your house.
Right. The second question, and this is also one of the foundational challenges of a wind turbine, is what happens in here. So we talked about charge controllers for solar, which is a little bit different because you kind of had mentioned on a really cold day, hot day, maybe the voltage changes or like the sun just starts to rise compared to high noon. You've got this pretty largely linear sort of distribution. And so maybe the voltage here is 20, maybe the voltage here is 30, and you've got these set points where the charge controller can say, when it gets closer to that, switch over to this voltage and this current, and it'll pick the most optimum path to get you your DC.
Right.
How does it change for wind?
Wind is exponential. So when you start out at 0, you're down here at the bottom, and then it grows on an exponential curve that is very, very difficult for a lot of people to get their mind around, because you don't start producing what's called usable power until you're somewhere around the 12 to 15 mile per hour range. So if we say this is like 12 mph for a specific size wind turbine, at 12 miles per hour, you might be getting, let's say, 35 watts of power out of that in a constant 12 mile per hour wind. But by the time you're at, say, 18 miles per hour, you might be getting 100 watts. So it's not a linear curve like this, it's an exponential curve. And then at 25 miles per hour, you're getting, say, 430 watts. Most people in the United States have average wind speeds in here, in this range, and that's the real big challenge here. We want to be able to capture and rate our turbine here at 25 miles per hour, and we want to be between 400 and 500 watts of output at 25 miles per hour. But we don't want to ignore the large lion's share of where they get their wind. A lot of people will buy a 2,000 watt wind turbine and think they're going to get all this power, but they're not getting anything because the wind is down here. In some ways, I feel like we're reinventing the wheel. There are charge controllers out there, but they're not optimized for VAWT, vertical axis wind turbine technology. They're all rated for a much higher RPM range of horizontal axis wind turbines.
Got it.
So we've got a unique challenge ahead of us.
Absolutely, yeah. No, this is, it's the opportunity and it's the challenge. That's
right.
Often coupled.
Yeah, and the Savonius is sort of the king of low wind speed power production, so we can produce power. You're seeing it here in a 7 mile an hour wind. That thing is definitely producing, wattage. It's just how do we capitalize with our generator and our charge controller on scavenging that for the end consumer. So we don't want to ignore that wind just for the purpose of getting 25-mile-per-hour winds, which might happen twice a month,
Right.
in a thunderstorm or whatever.
So this Savonius turbine works in a principle called differential drag. The air that comes on this side of the axis is just going to get diverted around with minimal impact. But here in the scoop, you're going to hit it and it's going to redirect it and push it and give you rotation. Now, in terms of efficiency, there's a number called Betz's limit, which we should talk about, which is the theoretical limit of how much energy any wind turbine could extract from the incoming wind. And that percent is about 60%, 59.3 to be exact. That means no matter what, vertical axis, horizontal, up high, large, small, whatever you have, you can't get more than 59.3% of the wind resource. So the large scale wind turbines that you see, like the offshore wind, the massive ones, those are able to get about 75 to 80% of Betz's limit. So about 45%-ish overall. How good are these? Well, this is a little bit of a controversial thing because there was some mismatched data we'll talk about, but ultimately these are about 30%, which is not bad, pretty close to the large scale systems. But the really amazing part is these work in a completely different envelope than large scale horizontal axis wind turbines, because these work on lower, slower flows of air and dirtier air. These can spin in airspeeds of 5 miles per hour, where typical wind turbines would not even be moving. And they obviously will perform even better at speeds of about 25 miles an hour. I think that would be the ideal maximum energy spot, but these work in a large variety of applications. Remember when I mentioned there's a little bit of a controversy about how efficient Savonius wind turbines are?
Yeah.
Check this out.
This is a signed copy by the author himself, back in the 50s when this was first published, where they began making this mistake. So they have the Savonius rotor and the American multi-blade turbines. The labels are in the same spots as they were in the original, but they drew the lines incorrectly. So back then, in the very beginning, when they did this research, Savonius turbines were actually rated up in the 32-33% efficiency range.
So that arrow is wrong?
Yes, that arrow was
That should be pointing there?
Yep.
And what about that? Where should that be pointing?
To the one down below. They just flip-flop those two arrows.
And so the thought process is if you're only about 10 to 15% efficient, that's okay, it's not bad.
Nobody's going to look at it.
But it's not going to be maybe worth any kind of investment.
Right.
But if you can get closer to 30%, then...
Yes, because your big multi-million-dollar turbines are only up here, and your Darius turbines are in this range. So look at that comparison between Darius and Savonius. If you can get into this range, now you're talking something that's far more worthwhile, worth investing money into.
And you have the signed copy.
Yeah.
There you go, if you're looking for some fun reading. So wind turbines are as amazing as we thought they were, and there's some pretty amazing research happening. Behind me is a 1 kilowatt home wind turbine that you could have. I mean, obviously it's pretty big, but it's not, I could probably fit that in my house. Or if you go a step down, you can have yourself a 500 watt or half a kilowatt. Now this would be the equivalent of maybe 2 solar panels, 1.5 solar panels. And it might cost a little bit more, but remember, a wind turbine is like a solar panel and a battery. Because if this is producing even 200 watts, right, over the course of 10 hours through the night, that's 2 kilowatt hours. That's 2 kilowatt hours you don't need to store in a battery. That means that anytime you can add some wind, you're not just replacing the solar component or adding to it, you're also helping with the battery, because you don't have to just charge the batteries in your house for a small period of time when the sun is shining and then have to run your house all night through a battery. Instead, you could additively add to your generation throughout the entire day with one of these. And that's why I've been wanting to get one for so long. So as soon as they're ready to ship and they're commercial, I'm gonna buy one and try it out because I'm just wildly curious. What do you think? Would you want to check this out? Would you buy a Harmony wind turbine or any wind turbine for your house if it was commercially viable and ready for us to do it? Sound off in the comments below. And if you thought that video was cool, check out this one next. And until next week, I'm Ricky with Vinci. Thank you so much for watching.